We begin. So now we've gotten down to here in our fine outline. And these two topics, Bayesian analysis and missing data analysis, not only do they fit very nicely into a 1.5 hours block, but they also go together very nicely thanks to the applications that we're going to take a look at. All right. So the reason we can describe Bayesian analysis so quickly is that all you need to know is this. So now it's time to go. If it weren't for missing data. Okay, so we do want to look a little bit into that black box and see what's happening, right? You're going to be confronted with the necessity of learning Bayesian analysis because many articles describe it. And it's not hard. It's much easier than mediation modeling. And it's always fun to peek into the black box and understand a little bit how things happen. And it's particularly fun with Bayesian analysis, I think. It's one of those topics like counterfactually defined causal effects in mediation that have, in my view, been portrayed in a much more complicated fashion than it needs to be. We're going to say these things in what we consider a simple way. True Bayesians may hate us for how we say it, but I think it works, and it's okay. We're going to now talk about Bayesian analysis and point out how it's advantageous to use it in some cases as a complement to ML, to maximum likelihood, which doesn't perform well computationally in all situations. And to do that, we're going to talk about priors, likelihoods, and posteriors. And we're going to talk about iterations and convergence in Bayesian cases and plots and model fit, and give several examples. So, why do you need to have one more thing to learn? Well, you do have to, because there are 6 great reasons to learn it. And here they are. So now, first of all, definition, frequentist analysis, that means maximum likelihood or weighted least squares, for instance. And any other analysis is non-frequentist, and Bayesian is very non-frequentist. There's actually been a war between Bayesians and frequentists for a long time. And it starting to calm down now. I would say that almost half of the statistical articles being published these days are based on the Bayesian estimator, not the maximum likelihood estimator. And why is that? Well, 6 reasons. First of all, I claim that much more can be learned about parameter estimates and model fit. So parameter estimates in maximum likelihood, you get one parameter estimate and its standard error. With Bayes, you get the whole distribution of that parameter estimate. True, you can get that in maximum likelihood if you add bootstrapping, but that's just it. You have to add bootstrapping to get that whole distribution of the estimate. In Bayes, you get it right away. Model fit in Bayes can be much more elaborate than in maximum likelihood estimation. You could look at any aspect of the model, any piece of the model fitting the data well. And you can do that through a concept called PPC, posterior predictive checks, that Gelman and others have come up with. We're going to talk a little bit about that, but not much today. But it's a general approach that can be applied not only in the overall fit, but in fits for different specific pieces that you want to get right. For instance, estimating the probability of 0 counts or something like that. And I claim that large sample theory is not needed for Bayes. In ML it is. In ML, when you have a parameter estimate and a standard error, and you do plus minus 1.96 times the standard error to get your symmetric confidence interval, you're really assuming, first of all, that the sampling distribution of the maximum likelihood estimate is normal, symmetric. And that's not necessarily the case unless you have a large sample. For Bayes, you don't have to have that assumption. The posterior distribution is always right, and it's often non-symmetric. I also claim that small sample performance for Bayes is better. That's a little bit more controversial. There's been a couple of applied articles written about that. That is if you choose the right, appropriate, weak priors, which I'm going to get to. But there is at least a hope that small sample performance can be better with Bayes. For instance, if you have multi-level modeling, 2-level modeling with rather few 2-level units, rather few clusters. Like, for instance, 10 clusters. Typically, we want to have 20, 30, 50 clusters for 2-level modeling. but maybe you can get away with fewer and still do well in Bayesian analysis. And in Bayesian analysis, you can work with priors. Prior is something that frequentists tend to hate, but you can make priors your friend, and you can use it in a way to build on previous studies, sort of in a meta-analysis fashion, where you have a population for which you repeat an intervention over time, and then you learn from the previous intervention the results of the effects, and they can become priors, more or less stringent informative priors for the next study. We're going to talk a little bit about priors that are informative in this fashion, but we're going to talk much more about the Mplus default of non-informative priors, which do not offend frequentists. And I would claim that Bayes comes in very handy in some cases where ML would be computationally demanding. We've seen examples where ML requires high-dimensional numerical integration. For instance, when you have binary factor analysis, you have a continuous latent variable, the factor, and you have binary indicators. Maximum likelihood then needs to compute the probability of the indicators, so it collapses, integrates out, remember these terms now, integrates out the factor, so it has to integrate. That's if you have one factor, it's one dimension, it's easy to do computationally, but when you have, say, 5 dimensions, it gets very heavy to do computationally, it takes a long time, and you lose a lot of precision, not only in the estimates, but also in the log likelihood, so that big comparisons become less dependable. So Bayes is useful. It avoids numerical integration. And then you have cases where maximum likelihood is pretty much impossible. And then Bayes, with its non-informative priors, can be viewed as a computing algorithm. That would give essentially the same results as maximum likelihood if ML were computationally feasible. So that's a very strong point for Bayes. And then point number 6, new types of models can be analyzed where ML is not practical. And we put tomorrow and Friday's topics in that category, DSEM, at least in a case where you have a lot of random effects, which we will have a lot of tomorrow and on Friday. A lot of random effects, a lot of parameters that vary across people. In that case, maximum likelihood would have been a hopeless estimator for DSEM. And tomorrow and Friday, all we're going to talk about is Bayes. Tomorrow, how many of you will be here tomorrow also again? How many of you will not be here tomorrow? Okay. Well, then you have the chance of hearing this Bayes story twice. So after lunch tomorrow, I talk about this topic again with a few additional twists. So if you want to take a long lunch tomorrow, you can have half an hour extra if you pick up everything I say today. So we're going to look at 2 cases here, informative and non-informative priors. Once again, this is the Mplus default, but you can also specify your informative priors for Mplus. So what you're looking at here is a one parameter on the x-axis. You want to get the parameter estimate. You want to determine where on this x-axis lies the parameter estimate. If you used ML, it would be where the likelihood has its peak. The likelihood describes the data as viewed from the prism of the model. So when the likelihood has its peak, that is when the first order derivative is 0, that is where the parameter estimate is according to ML. But you can have a prior notion based on previous experiences, pilot studies, that describes the distribution of a parameter. And this is heresy to a frequentist, because a parameter is a fixed value to a frequentist, but to Bayesian, a parameter has a distribution, a prior distribution. Before you collected the data, you have the notion that, yeah, most values for the parameters are likely to be around here, but you're uncertain, so you have a certain variance around that mean. So instead of having the maximum likelihood value here, Bayes weighs together the prior and the likelihood to create something called a posterior. In this case, the peak lying somewhere in between of the prior peak and the likelihood peak. That's how it works. Now, if you have a non-informative prior, then you have a prior with very large variance, infinity perhaps, in which case there is no difference really in the peak between the posterior and the likelihood peak. They would fall approximately at the same parameter value. And that's the Mplus default. So even though the priors are uninformative, non-informative, or diffuse, we benefit from them in the computational algorithm that Bayes provides compared to ML. So as the prior variance increases, the Bayesian estimate gets closer to the maximum likelihood estimates. Yes. And then the informative priors, they are priors where the variance is not huge. And the smaller the variance, the more certain you are about what you think the parameter estimate will be, coming from substantive theory combined with previous studies of similar populations. In between, we have weakly informative priors. And that is used more or less to help the iterations, the computations of the estimates from a technical point of view, which in some cases can veer off in the wrong direction if you don't guide them. If you know, for instance, that it's impossible that a value is greater than -1 to +1, we can have a prior that more or less forces it, the true value, to lie in that area. So that's a weakly informative prior. We use that for thresholds in categorical variable modeling. We're not going to talk much about that today. Now I introduce you to trace plots. So you're going to get to know a lot of new words here. A trace plot is a plot that shows on the x-axis the iterations. You iterate, just for like for maximum likelihood, you iterate, you get closer and closer to a final product. And so you have the iterations on the x-axis here. You can see this in Tech 8 also. On the y-axis, we consider a parameter, the values of a parameter. In this case, it's mean. And a starting point could, for instance, be up here, the listwise deletion estimate, a very rough estimate, not maximum likelihood, not Bayes. And then we're going to iterate our way through here over the iterations. And what this does, it doesn't just end up with one estimate that's correct, not just one estimate that's in ML. What you're getting here is a distribution. Do you see the distribution? No, you don't, because you have to tilt your head to the left like this. And then you can see that the points fall down into most points lying in the middle here, and some points at the extreme parts, the tails. So if you don't feel like let's see, I have to do this way, right? If you don't feel like tilting your head, you can look at this little movie instead. So here we have a trace plot for two processes, and you have it develops like this. And there are the different iteration points, and then you turn your head. And you don't only get an estimate, but it falls down into a distribution. And that distribution has a mean or a median and confidence intervals, and it's non-symmetric. Yes, this is right. So let's look at that again. So what's happening here is we have gone many more iterations than the 30. We have gone way over here. And there's a line here, which is the line where you discard the iterations early on here because they haven't stabilized. So you only use these iterations, those values, for the posterior distribution. So that's called the burn-in period. So that's automatically discarded by Mplus. So let's play the movie again, but perhaps a little faster. Maybe you should have subtitles. Anyway, now you will forever remember how the posterior distribution comes about, right? The movie. All right, enough of that, right? So here you have it again. You have the, this is the trace plot, and there are two iterations going on at the same time. That's the default in Mplus. We'll get back to that in the Mplus input. And we throw away these early iterations because the process has not stabilized, and use only the iterations after this burn-in period. To make sure that we have converged, we want a so-called potential scale reduction value close to 1, which means that the between chains, you have two chains, and one blue and one red, I believe, between chain variation is small relative to the within chain variation. That makes sense, right? Within chain variation is the natural variation over the posterior distribution. But you don't want different chains correspond to different starting points. You don't want the between chain variation to be large relative to the within chain variation. You want it to be small. So when PSR comes down towards 1, you will conclude that the process has converged, and it's not only one estimate that is converged to, it's converged to a distribution very nicely. So now there are many other ways to judge convergence, and maybe in the future we'll output the information so we can take it into standard convergence software like CODA, C-O-D-A, Nikki Best and others, connected with the Bugs project in the UK. Who knows? One warning, though, when you use this in practice, and this is an important warning, you have the PSR, that convergence criterion, which is supposed to go down to 1 for convergence. X-axis is the iterations. We call them MCMC for Markov chain Monte Carlo. That's a particular algorithm for Bayes. So we have a very high PSR value early on, not converged at all, and then it goes down to 1. And sometimes, by mistake, you may stop here. Mplus may stop here unless you forced Mplus to go beyond this, because then PSR goes up again and doesn't calm down until over here with many more iterations than you had over here. So you have to make sure that PSR has been at the value 1 not only a short period, but a long period like that. And here you can see this Tech 8 screening, screen printing. You have the iterations here. We only record every 100th. You have the potential scale reduction, which starts out pretty low, but lo and behold, it goes up here and then down, and you might prematurely stop here, but then it goes up again to 1.2 before it starts coming down. So you should go on very much further. Maybe you want to force about 5,000 or 10,000 iterations. And you can see here which parameter has the biggest problem. That's always indicative of, or often indicative of, which parameter is hard to nail down. That's a technical term for estimating it well. And you see the time here, again, per iteration, so that you know if you should just go out and have a cup of coffee or take a walk or make it run overnight. Now, the trace plots also show you mixing. Mixing meaning you have a posterior parameter distribution, and you want the iterations to visit, as the Bayesians say, visit every part of this posterior distribution, are out in the tails, everywhere, so the distribution is well described. Good mixing, the trace plot looks like this. Here's the burn-in demarcation again. So it's, some people call it the caterpillar. It's horizontal, zigzagging up and down. This is poor mixing. It looks like there may be two estimates, one low and one high here. And you see this trend, this autocorrelation going like this. You don't want to see this. You want to see that. Try to come up with simple rules here. And then you have a distribution of values for the parameter. And just like in regular statistics, you want the observations, the points in the distribution, to be independent, random sample type of thinking. So we record the autocorrelation with lag 1, 2, 3, up to 30 here. And low autocorrelations indicate independence of the draws for the posterior distribution. So this is very good. This is very bad. This is a difficult model, poor mixing. And you may want to skip over some iteration, only record every 10th or every 100th using the so-called thin option, T-H-I-N, thin option, to avoid this, to make this look like that, although it would be hard in this case. Bayes posterior distribution looks like this. It doesn't have to be symmetric. We get the whole distribution, so we can easily find the percentiles, the 3.5th and the 97.5th percentile, and therefore we get this 95% interval here, which the Bayesians don't call confidence but credibility intervals. And for most cases, the Bayes distribution will be very similar to what you would have gotten had you been able to, or if you had used ML. This is ML by bootstrapping, and this is Bayes. So you get the same idea here of wanting to see the whole distribution. Speed of Bayes, there was an article in Structural Equation Modeling where they compared, it was moderated mediation, very apropos topic here, and they found that ML with bootstrap and Bayes gave very similar statistical performance. So you don't have to worry that all of your results are going to be different now when you know to do Bayes. In fact, you can just feel more confident about the results when they are so similar. And you can also see which small differences between them you shouldn't pay attention to. That is, the precision with the maximum likelihood estimate, you get a feeling for how precise that is when you do Bayes, and it's not exactly the same. Now, they also compared speed, although that was not in the article, unfortunately, but Mplus was 15 times faster than bugs. And it's faster than other programs like JAGS and STAN too, I believe. And the reason for Bayes being faster is mainly because Tiomer programmed it. And he uses Fortran and parallel computing. So they compute each chain in parallel. And large updating blocks, meaning that you, in the iterations, which I haven't described, I'll describe more in technical aspects of that tomorrow, you pair together parameters that may be highly correlated. So it's more complicated, tailor-made code, but that then beats just standard applications of bugs. And also Mplus Bayes is considerably easier to use than, I think, most other Bayes programs. So the advantage over ML is also in informative priors that you can better reflect substantive theory. But we're not going to talk much about that today, except for having one example of it. So the examples are going to be first a non-informative prior example, and second, an informative prior example. And I think that means that I should be yanked off the stage. Thank you.